Hello everyone, welcome back in the next video in the series of linear algebra question of GATE exam. So now let's start the video with question number 1. So question 1 says a system of n homogeneous linear equation containing n unknowns. Okay, here we are given a system of n homogeneous linear equation. So we have sorry we have n equation 1 up to we have n equation and linear equation containing n unknown. We have n unknown. Let's call it x1, x2, x3 up to xn, and they are homogeneous. So we have to equate equal to 0. Now here maybe some constant are there. So they're asking about the will have a non-trivial solution if and only if the determinant of coefficient matrix is okay. So they're asking about the condition of this coefficient matrix, which is formed with the help of this left hand side of this equation. So now if we recall, for any homogeneous system we have at least one solution, and which is trivial one. And if we put all the values here, x1, x2, x3 up to xn, this all variable, let's form in this vector form. Here we have n unknown, so I can write x1, x2 up to xn. So I have formed the vector of this all unknown. And if let's say this vector has all this variable has 0, so in other word, this vector is 0 vector. So now if you put all the variable on the left hand side are 0, then you automatically get right hand side, and which is 0 in the homogeneous case. So the homogeneous system is always consistent, and the solution of this kind of all variable are 0 we are calling a trivial solution. So now if uh, we recall the solution of simultaneous linear algebraic equation with the help of matrix, then we know from the basic concept, if the if we represent our system of linear equation in this ax equal to b, and here this a is coefficient matrix, and now here this x is our variable vector, and now here this b is nothing but the right hand side of this all simultaneous linear equation. So now from the concept of solution of simultaneous linear equation, we can say if the determinant of any coefficient matrix will be 0, then the two possibilities are there. And what are those? So let's write one by one here. If the determinant of this coefficient matrix, here I am denoting as matrix A, is 0, then the two possibility are there. First possibility says there are no solution for this system. I am talking about any general simultaneous linear equation, set of linear equation. The first condition is there, and the second condition is there is infinite solution of any particular system of equation. So now here it is given that the system is homogeneous. That means here this vector b is in this form 0 0. So this possibility of no solution will automatically cancel out, because here the system is homogeneous, and homogeneous system is always consistent. So the only the remaining condition for this determinant equal to 0 is just infinite solution, and that's mean this solution are basically non-trivial, because we are getting a trivial solution for any general homogeneous system. It is always there. So this infinite solution means this x1, x2, x3 are non-zero. So now the condition is they are asking about the condition of this coefficient matrix in terms of determinant. So it must be 0 to get non-trivial solution. If it's non-zero, then we are getting a solution as trivial solution, which is in this term 0 0 vector. So now the correct answer for this question is 0. Now let's move to the question number 2. Okay, so question 2 says the product of the eigenvalue of a matrix. Okay, we have given a 2 cross 2 matrix. If you recall the property of eigenvalue, then we can say the product of all eigenvalue of any particular matrix is just simply the determinant of this matrix. So here in short they are asking about the determinant, but they have written in this form the product of eigenvalue. But in the simple word they are asking just simply the determinant of this matrix. So let's find it here. 14 minus 0, so determinant is 14, which is in turn the multiplication of these two eigenvalue. Let's call it lambda 1 and lambda 2. So we have find out the product of these eigenvalues, and which is 14. So I have to write it here. So very simple question. Okay, now let's solve question number 3. Question 3 says for any real, square and non-singular matrix. Here recall, non-singular means determinant is not equal to 0, because the word is here non-singular, and non-singular matrix B, then they are asking about the determinant of this inverse matrix B inverse. So now we know from the basic concept of this inverse matrix that the determinant of any inverse matrix, it is just simply the inverse of determinant of original matrix. So now here the original matrix is B, and the I can write like this, here determinant of B, and I have to take the inverse of this to find the determinant of inverse matrix. So option C correctly describe the inverse of this, sorry, determinant of this inverse matrix. So option C is the correct answer. Let's move to the question number 4. Okay, question 4 says the value of x3, here x3 is a variable, obtained by solving the following system of linear equations is called what? Okay, so we have to solve this three linear equation to find the value of x3. So let's first of all write in this matrix form x equal to b. So now here a is nothing but the simply coefficient matrix. So I have coefficient 1 1 minus 1 in this first equation. I have value 2 1 1 and 1 2 minus 2. So I have formed the coefficient matrix. Here in the place of x I have to put the vector in this form of variable. Here variable are x1, x2 and x3. And now on the right hand side we just simply have to put the right hand side of this equation in the same order, 2 minus 2 and 4. So now we have written these three equation in this matrix form. So now the next step is that we have to form augmented matrix from this. Augmented matrix. And how we form the augmented matrix? We just simply bring this right hand side very near to this matrix, this coefficient matrix, and we remove this this vector in this, which are in x1 x2 x3 form. So let's form the augmented matrix. Here minus 1 1 minus 3 2 1 1. Let's I am putting a vertical line to distinguish this coefficient matrix and this right hand side. Let's bring it here. Okay, so we have formed the augmented matrix. We call this types of matrix as an augmented matrix, specific name for this matrix. So now here for finding the value of this unknown x3 we have to perform some row operation. So now we have to reduce this number as 0, and this number is also 0, and these two will also we have to reduce 0 to find the to easily find the all the values of this unknown x1 x2 and x3. So now here let's write what we are going to do. Let's if I am adding 2 times this r1 in this one r2, then here this element will be 0, because here we have plus 2 and minus 2 we will get after multiplication this row with plus 2. So again this entry after the addition is 0. So I can write r2 plus 2 times r1 form new r2, and now in the same way let's add this r1 in the r3 and it's give me a new r3. So now after this two row operation what we are getting, let's write quickly here. The first row will remain as it is, here 2. Now here let's multiply this row with plus 2, so minus 2. Here we are getting 0, and here we are getting again plus 2 because we are multiplying this first row with 2 and here we have already 1. So after addition we are getting 3 here. Now here we are getting minus 2 and we have already plus 1. So we get minus 1. Now here we are getting plus 4. We have already minus 2. So after addition we are getting plus 2. Now in the third row here again we are getting 0. Here again 3 and here we have to just simply add this entry in this minus 2. So minus 3 will be there and this minus 2 going to add in this plus 4. So 2. So now to further reduce this entry as 0 to reduce it into echelon form we have to further do one more row operation which is just simply let's subtract this r2 from r3. So I can say r3 minus r2 make new row 3. So after this row operation what we are getting, the first and the second row will remain as it is because we are only performing the operation in the third row. So now here this entry is already 0 and here again I am getting 0 and here let's multiply this entry with minus sign. So it will be plus 1 and let's add in this. So minus 2 and let's multiply this with minus sign and add in this 2. So again here 0. Now recall we have here the let's further form the from this step further form this matrix in this form this variable. So now here I can write this coefficient matrix as it is. Here I in the multiplication with this variable vector on the right hand side I can write this. So now if you do this and if you again write the equation from this system and you will find the value of x3 easily. So here we can say this coefficient so minus 2 x3 because here this entry will multiply with here and here the variable is x3 so minus 2 x3 and it equal to the right hand side and right hand side we have 0. Remember this column is corresponding to the right hand side of this equation so I can say equal to 0. So I can easily say that value of x3 is 0 here. So now we have find out the value of unknown x3 with the help of back substitution. You can also find the value of the remaining two variable which are x1 and x2 because we are going from the x3 to x2 to x1 we call it back substitution because we are going from the bottom so we call it back substitution. So we have find out the value of unknown x3 here which is 0. So option A is the correct answer. Okay, now let's solve question number 5. So question 5 says the determinant of this 3 cross 3 matrix. We have to find out the value of determinant. So if we directly expand, it is little bit complex to solve furthermore because here this determinant has some unknown in terms of b. So here look at this last column. Here these entries are same, so we can easily make these two entries equal to 0, and we can just after that we can easily solve the determinant in single step. So here first of all let's perform some row operation, and we know why any row operation or column operation the value of determinant will remain unchanged. So now here let's write it here what we are going to do. Let's subtract r1 this from r2. So r2 minus r1 will makes new r2, and again let's subtract r1 from r3. So it will make new r3. So now after this two row operation what we are getting, let's write it here. The first row will remain as it is, and now here I have to subtract this 1 plus b from this b. So here I am getting minus b. So we have already plus b. So minus b and plus b will cancel out and we are getting minus 1. Now here this minus b will cancel with this plus b. So again 1, and here this 1 will cancel with plus 1. Here we are getting minus 1 after multiplication. So now in the third row here this 1 will cancel with this minus 1. Sorry, this minus 1 cancel with this plus 1 and we are getting minus b. Now here I have plus 2b and minus b comes from the first row. So plus b, and here again 0. So now it is very easier to find the determinant. because here we have two entry as 0. So let's find the determinant. So I have to put this first term and multiply it with multiplication of this 2, subtract from this, subtract multiplication of these 2. So I 0 again 0, because these two entries are 0. In the same way b, and I have to multiply it with determinant of this second order minor. Again the entries are all 0. So now the last entry will be 1 multiply with the determinant of this minor of this two second order. So here minus b, again minus b, and we have to put the minus in between, so it will be plus b. So now this minus b cancel with this plus b, so again determinant is equal to 0. So now the value of determinant for this matrix is just simply 0. Okay, now let's move on the question number 6. Question 6 says if A is a square matrix, A is a square symmetric matrix, and recall the definition of symmetric matrix. If I am taking the transpose of any matrix and I get the transpose is exactly same as the matrix itself, then I am calling this matrix A as an symmetric matrix. Symmetric real matrix, because all values are in this matrix are real. So now it is given that the matrix A is, it is already given in the question that this condition is going to hold. If A is a square symmetric real value matrix of dimension 2n, okay, we have given the dimension of this matrix, and here the matrix is always square matrix. So here the dimension is 2n, so it means it has 2n row and 2n column. Then the eigenvalue of A are, okay, they are asking about the condition of eigenvalue. So now recall the property of this symmetric matrix. It's all eigenvalue. Let's write it here. For, let me change color. For any real symmetric matrix, its all eigenvalues are always real value. So now it is the property for real symmetric matrix. So now let's go through this four option. Option says is n pair of complex conjugate number and not necessarily distinct. So again this statement is wrong, because the matrix is real symmetric, and we know from the property that it has only real eigenvalues. So now let's move to the option B. Option B says 2n real values not necessarily distinct. Yes, it is the correct one, because we know that at least 2n eigenvalue are there, because the number of eigenvalue are equal to the order of any square matrix, and here we are not sure about the this distinction without further more detail of this matrix. So it may be distinct or not, but here it is given in the option B, not necessarily distinct. So option B is the correct statement regarding to the eigenvalue of this any real symmetric matrix. Let's also check option C and D. Option C says 2n distinct real eigenvalue. So now here it is given that the eigenvalue are distinct, but here the condition is that values are always distinct, but here it is not, maybe case sometime it is depend on the particular matrix, so we cannot say this statement for any general matrix. So option C is also not correct one. Option D says n distinct pair of complex conjugate number. Again we are not getting any complex number in the eigenvalue, because the matrix is symmetric and real. So the only option B is correct for this condition. So option B is the correct answer. Okay, now let's solve question number 7. So question 7 says Q1 q2 up to qm are n dimensional vector. Okay, here it is given that this q1 q2 up to qm are the vectors and whose dimension is n. So let's form one vector. Let's q1, so it has entries, n entries, because it has n dimension. So I can write like this: x1 x2 up to xn, and here the variable x can take any values. So here in this term I have m vector like this. So I can write like this. So here the it is given that the number of equation here, this number of vector which is m is less than the number of entries in any particular vectors which are n. So condition is given that the number of vector which is m is less than the number of entries in any particular this vector, this vector q. So they're asking this set of vector is linearly dependent. Okay, the condition is given that this set of a set of vector are linearly dependent. That means let's arbitrarily assume any q, let's call it q5 for just simple example. So I can write this q5 as in some constant times q1 plus second constant time q3 plus third constant time q4 plus up to some another arbitrary constant time qn. So I can form this q5 vector with the help of this other vector in this linear form after multiplying this some scalar here, and here it is given condition, necessary condition is that this all variable c1 c2 c3 up to whatever value it may be are non-zero. It is necessary condition for the linear dependency, this scalar must be non-zero. So now here the condition is given in this form. From this statement we can draw conclusion like this. So q is a matrix. Okay, they have formed the matrix q with the help of this m vector. So I have to, what I have to do, let's write it here q. So what is the matrix q? It is stated in the question, q is the matrix with q1 q2 up to qm are column. Okay, so this matrix q is formed in such a way that this vector will form the column of this matrix q here x2 and up to xn. In the same way here I have to put the element of this q2. In the same way I have to put the element of q3 q4 and up to it will go to the qn, and this is the our matrix q. And let's let's check for the dimension of this q matrix. So now what is the dimension? So here I have to first of all find the number of row, which is n, because it has n entries. So x1 x2 x2 sorry x3 up to xn. So I have n rows, and what is the number of column? Because I have m vector here qm. So I can say q1 q2 q3 q4 up to qm. So I can write the order as n cross m, and here the condition is given that value of m is less than n, which means number of column are less than the number of rows. And now so they're asking about the rank of this matrix q. They're asking rank of this matrix q. So now here the condition is given that this set of vectors are linearly dependent. Then what does it mean? Simply, if we perform some column operation on this matrix, then we can easily reduce at least one column in this 0 0 form. Let's take again the example of this. Here we have assumed this q5 vector q5 is linearly dependent on the other vector. So here I have written the q5 matrix in this column form. So now if I am performing some column operation on this column with in this form, I have multiplied this column with c1 constant, this column with c2 c3 c4 and up to here c prime, and I am subtracting this all vector addition from this one. So here I am getting all entries as 0, because it is exactly same as q5, because q5 is nothing but the linear combination of the remaining all other vectors. So I am simply just getting here 0 0 vector. So now at least I am sure here that the rank is must be less than 1, then the number of minimum dimension here. First of all we can say the condition about the rank of q is it must be less than or equal to of minimum from its dimension. Here the dimension is n cross m. So here I can say the rank of q it less than or equal to, I have to choose the minimum from these two, and it is given that the no, m is minimum. In the other word, number of column is minimum. So I can say the rank is less than m here, less than or equal to. But here the in the option they have state only written the less than here. So for further that I have to remove this equal to sign to reach the solution. So now here we have determined that at least one of the column of this matrix will be 0. Then we can subtract from 1 from this one. Then the rank is automatically less than m. So I can write the rank of q is less than m is equal to sign will goes because because at least one of the column is all as 0, all entries as 0. So we draw the conclusion that the rank is less than m. But how much is less is depend on the this further entries of this element. We cannot directly say it, but we are sure that the rank is must be less than m. So option A is the correctly describing this condition. So option A is the correct answer for this question. Okay, now let's solve question number 8. Question 8 says which one of the following statements are true. So we have four statements in terms of P, Q, R and S. So first of all let's go through the statement P. Statement P says the eigenvalue of symmetric matrix are real. Yes, it is the case because we have seen in this in video in I think question number 6 or maybe 5. So the eigenvalues of any symmetric real matrix are always real. So option A is the correct statement. Sorry, statement P is the correct one. Now let's move on the statement Q. Statement Q says the value of determinant of orthogonal matrix can be plus 1. Okay. So here it is given in the question, sorry, statement Q that the determinant of orthogonal matrix plus 1 will be plus 1. So now here for the orthogonal matrix, what is the definition of orthogonal matrix? If I am multiplying any matrix with its transpose and after multiplication I am getting the identity matrix, then I can say if this condition is going to hold, then I can say this matrix A is orthogonal matrix. But now they are asking about the determinant. So now let's take the determinant both the side of this equation. So I can write here determinant of A times A transpose it equal to the determinant of identity matrix. Now further from the property we can write from the equal this left hand side equal to the multiplication of individual determinant, which is determinant of A multiplied with determinant of A transpose, and on the right hand side we have 1 because the determinant of identity matrix is 1. So now again we can say that the determinant of any matrix A and its transpose are exactly same. So here I can write determinant A square will be 1. So let's find the value of determinant. So here I am getting as in plus or minus 1, but in the statement it is given that it can be only plus 1. But here if this condition is written in this way, this plus or minus 1 instead of plus 1, then this statement is true. But here it is written as only plus 1. So statement Q is not true. It is only half true because the only one case is given. This minus 1 is missing. So statement Q is not true. So now let's move to the statement R. Statement R says the transpose of square matrix A has the same eigenvalue of those of A. Yes, it is the correct one because we know that the determinant of A and A transpose are the same, and we also know that the multiplication of all the eigenvalues for any particular matrix is nothing but the determinant of its matrix. So from this you can also check for any matrix after taking the transpose, that its eigenvalue are exactly same as of those of transpose matrix eigenvalue. So statement R is again true. So now let's also check for the statement S. So S says that the inverse of n cross n matrix exists if and only if the rank is less than m. Okay, we have a many matrix of general order n cross n, and it is given that the inverse matrix, let's call it matrix A. It is given that A inverse exists only if the rank is less than m. And what does it mean that rank is less than m? That means it has at least one row as all entry as 0. Then the determinant of this matrix A will be 0. So now it is the singular because determinant is equal to 0. So we are calling it a singular matrix. Singular matrix. And recall the formula of inverse. A inverse, it is nothing but the 1 upon determinant of matrix multiplied with adjoint of matrix. And here the determinant is 0. So this right hand side will be indefinite because we have put the 0 in the denominator. So we are not getting inverse for this case. So now it is the exactly the wrong statement. If the rank is exactly n, then and then is inverse is possible. But here in the option, in the statement it is given that the inverse is exist if and only if the rank is less than n. So it is the absolutely wrong statement. So now from the option we can say P and R are the correct statement. So P and R only. So option B is the correct choice of the statement which are true. So option B is the correct answer. Okay, now let's solve question number 9. Question 9 says consider the following 2 cross 2 matrix. Which one of the following vector is not a valid eigenvector of the above matrix? Okay, so first of all, recall the basic definition of eigenvector. If I am multiplying any matrix with its any eigenvector, then after multiplication I am getting the same vector, but its magnitude is just simply change. Now if let's draw it in the xy plane, or it simply state that. So now let's assume I have any vector x here. Let's call it an vector x. It has some arbitrary value. So now if I am multiplying this vector with this matrix A, and A has any value, in this particular case it has value of this. So let's write it here: 4, 0, 0 and 4. So now what does this condition means in this xy plane? So here I have x axis and y axis, and if I am multiplying this matrix with any vectors, let's call general, let's write it in the general way. Here we have vector in this way, and let's it has any general vector in this form x1 and x2. Let's write in this x and y term. So I can write here x and y. So if I am multiplying this matrix with this vector, then in the output I am getting the another vector which is again 2 entry. But this vector, it may be rotated at some arbitrary angle after multiplication and scaled some different magnitude. So now first let reduce this x and y with this another of any arbitrary value. So let's say I have as here entry as 1 and here also as in 1. So here what I am getting 4, here 4 also. So you can see I am getting the same vector which is parallel to this x vector, but its magnitude is different. So let's draw it here. I hope you understand this. So my new vector after multiplication is like this. It is exactly coincide with this initial one, but its magnitude is 4 times this x vector. Its magnitude is 4 times larger than this one. So if this is going to hold, the vector is not rotating in this xy plane, but it's just simply the scaled by some magnitude, some scalar. Here the scalar is 4. So now let's take another example. Here I have vector 4, I have matrix like this, and let's multiply some other vector. Let's call it 2, 3. So I have, let's draw first of all in this xy plane. So the here vector look like this in this xy plane. Sorry, it will look like this. Let's also make it green to understand easily. So now let's do the multiplication. Again, what we are getting here 8 and here 12. So now you can see I have x coordinate as 8 and y coordinate as 12. So now if I want to draw this, then I have to draw like this. This is the our new vector after multiplication. Its magnitude is changed, but it is also rotated by some angle from this initial one. Let's call it theta angle. But now in this first case, this one, this vector, it is not rotating in the space, but it is just simply scaled by some factor, and this factor particularly here represent the eigen value, and the vector which is just after multiplying any particular matrix, it is just simply scaled in the magnitude. It is called a eigenvector. That is what this statement is state in this represent in this xy plane. I hope you understand this concept. So now let's back to our question and let's clear this all. So now let's back to the question and trying to satisfying this condition. We are looking for the option which is not satisfying this condition because they are asking about the not valid eigenvector. So let's first of all write the matrix which is 0 4 1, and let's start from the option A. So option A has an entry in the form of vector 1 and 0. So let's do the multiplication. So here I am getting 4 and 0. So now you can easily take out 4 common and represent this vector in this lambda time initial one. So again you can say here the vector is repeating itself here, but the magnitude is different. So I can say option A contains the correct eigenvector. Let's move to the option B. Let's write matrix A here as it is. I have to multiply it with vector given in the option B. So now let's do the multiplication. So here I am getting minus 8 and 4. So again you can easily take 4 common, and again you can represent this vector in this lambda time initial one in this form. Here the initial vector is this one. So again the vector is repeating itself and its magnitude is just simply change. No rotation in this xy plane. So this is again the eigenvector for this 2 cross 2 matrix. Now let's move to the option C. Okay, so option C has 0 0 entry in this vector form. So it is so simple. We are again getting 0 0 because vector here is 0. So now if this is the case, then we can say this 0 0 is the eigenvector for any matrix. But here let's again draw in this xy plane. What is this 0 0 vector represent? It is just simply the origin, because the value of x coordinate is 0 and the value of y coordinate is 0, and this is satisfied by this origin. So it is just simply the point, not any vector. So it is of course not valid vector, and that is what they are asking. So option C is the correct answer for this question. Let also check option D also. So let write matrix A here and let's multiply it with vector given in the option D. So again here we are getting 60 minus 12. Again you can take 4 common from this vector, and you can represent this vector in this lambda times the initial one. Here the initial vector is 4 times 1. So now if you draw this vector in this xy plane, so let's quickly do it. So now the initial vector is x coordinate has 4. So somewhere here let's call it 4, and the y coordinate is minus 3. So somewhere there. So it is our initial vector. But after the multiplication we are getting 4 times the initial one because it is just simply 16 and minus 12, so 16 will come at some further apart from this point. So I can, let's draw this a new vector. It is just simply the parallel to this vector. In fact, it is coincide with this initial vector, and it is continue up to this new point, which is 16 comma minus 12. So now we can say this vector is not rotating in the space after multiplication with this matrix, but it is just simply scaled by some scalar, and here the scalar is 4. So it is satisfying the definition of eigenvector. So option D is also contain the correct eigenvector, but the only option C does not contain the correct valid eigenvector. So option C is the correct answer for this question. Now let's move to the next question for this video. Okay, now question 10 says a set of linear equation is represented by the matrix equation. Okay, simply just we have set of linear equation and which is represented in this Ax times b, and here this A is nothing but our coefficient matrix, and here this x is our variable vector in some in the form of some arbitrary vectors, and this b is again the column vector of the right hand side of this all linear equation. So they are asking the necessary condition for the existence of the solution for this system is. Okay, so now what is the necessary condition? It must be that the solution of this system is exist. So now if you form, let's form a matrix here. I have a coefficient matrix here, and I have here variable vector, and here I have a right hand side. So now to here what I have to write, the all the coefficient of this x1. Let's assume we have three variable x1, x2 and x3, and I have to write here the coefficient of x2 of three equation. Let's also assume we have a three equation, and I have to write the coefficient of x3 here, and I have to write x1, x2 and x3, and here I have to write some arbitrary value which is present in this right hand side. So let's play by putting this here. So now if I am putting here equal to, then what does it mean? If I multiply some scalar to this vector plus adding this vector with multiplying some another arbitrary value plus adding this vector with multiply with another eigenvalue, and if I hold this all the value, then I am getting the this vector. This means this all the column are linearly dependent on this right hand side which is b, then and then the system is have a solution. So now I can say that b must be linearly dependent on column of a, because here the whatever it may be, it must be represented in this linear combination of this form. So let's I can write here b, here I have maybe any constant c1, and I have first column of this coefficient matrix plus some another constant times the second column of this coefficient matrix plus c3 times the third column. If this is going to hold, then and then we have solution for this system of equation, otherwise the system is inconsistent. So the necessary statement for the existence of solution, we can say that b must be linearly dependent on the column of a. So option A is the correct statement. Now let's further explain this furthermore for more clarity. So now let's assume here any arbitrary value. So I can write here I can multiply this value with this x1, this value with x2 and this with x3. So let's assume p here x1 plus, let's here assume p, q and r. So I have p q1 plus qx2 plus rx3, and I have to equate this equal to this right hand side that assume it has value n. So n, so here you can see these three number are these three variable x1, x2, x3 are any represent any scalar, and these three are linearly, this n is linear combination of these three p, q and r. So I can say this line addition of this these all columns are linear this vector n is linearly depend on this column from this uh, condition of this equation. In the same way, for this second row, I can also write the similar equation, and I can also prove that this second row is also linearly dependent on this right hand side and left hand side. In the same way, I can do for this third row, and I have to equate this equal to this one, and I can again say this entry is nothing but the linear combination of these three one. In the same way, this entry is nothing but the linear combination of these three entry, and this entry n is linear combination of these three here in this way. So I can, in nutshell, I can say this whole vector which is present in the right hand side is nothing but the linear combination of the column of this coefficient matrix, and which is given in the option A. So option B, again option B says B must be linearly depend on the column of A. So here B is written on the right hand side. So I can say this vector must be linear combination of this column of this coefficient matrix. So option B is the correct answer for this question. And that's it, and thank you for your support and watching this video. See you later in the next video. Take care of yourself. Bye bye.